After the lunch break, I have the honor to present some of my colleagues who will speak about IP protection in machine learning and AI. Rudolf Mayer is senior researcher at SBA Research and leads the machine learning and data management research group. He is also lecturer at the TU Wien and at the University of Applied Sciences Technikum Wien. Tanja S is also researcher at SBA Research, focusing on privacy-preserving data analysis. And in their talk, Rudolf and Tanja will now present us some state-of-the-art methods for watermarking and fingerprinting machine learning models, and also their vulnerabilities and challenges in protecting ownership of digital content. So please, welcome with me, Rudolf Mayer and Tanja S. Sorry, once again, Shachevich, I will get it. Talking about IP protection in machine learning and AI. Applause.
Okay, I hope you can hear me. Welcome to our talk. It's a nice pleasure to be here. Last year we only had a virtual talk. It's much nicer to be here in person. I will start with the talk. I will tell you a bit about what's the problem, and then Tanja will hopefully present you some kind of solutions. And basically our talk is all about IP protection along the machine learning pipeline. So I'm not sure how much you're in your job working with machine learning or AI or deep learning or however you want to call it. Maybe you're already working with it, maybe you plan to work with it, maybe your boss thinks that you will have to work with it in the next, I don't know, a month or two. So, but anyway, there's a lot of machine learning around us, and it's increasingly getting deployed in many settings. There's obviously a lot of hype around what machine learning supposedly can do, but there's also a lot of tremendous advancements. So it has a reason to be actually hyped. And in some cases, you can actually surpass human-level performance. There's many application areas: autonomous driving, medical diagnosis, machine translating, gaming, and any new thing that you want to hype, just say it also uses AI, and then people try to sell it better. So I said there's a lot of advances. So for example, medical diagnosis, already quite some years ago, there were some studies showing that for skin cancer diagnosis, you can actually really surpass human-level performance. Maybe many of you have heard about AlphaGo, where the system from DeepMind. Okay, I never get disturbed by Nikki, so that's good. Was actually able to beat one of the best Go players. Don't ask me anything about Go, I really don't know anything about it. And also autonomous vehicles, obviously going increasingly being deployed. Maybe you now have a lot of assistive technology that's not really yet autonomous, but it's using some kind of machine learning. And we're obviously getting closer and closer to autonomous driving. Don't know yet when it will be here, but there's a lot of advancements going on. One question about all of this is, what about security aspects? So it's not going to be a talk about only machine learning. This would be maybe the wrong venue. But what about security in machine learning? And you have heard yesterday in the talk from Jelena also a bit about risks that can happen in machine learning. And this is basically because security has not really been much a focus in machine learning until very recently. So the goal until now was to actually make things work so that you can actually effectively use machine learning systems, and they're reliable and they're generalizing well enough. But security was not really considered much. So people didn't really think what happens when you have adversaries in the system. So this is basically then what our talk will be about. First, I will briefly introduce you to a few concepts of machine learning that maybe some of you already know, but maybe it's good to refresh. And then we talk specifically on attacks on the intellectual property that you're creating and using in the machine learning pipeline. And then Tanja will talk about how to protect your assets. So if you think about the machine learning workflow, very simplified, you have normally two stages. You have a training phase that happens somewhere offline, where you have data, in this case, these types of fruits, and your task is obviously to think what kind of fruit is a specific data item. And for this, you also have labels. So someone sat down and said, okay, the first item is a sorry, the first item is a banana, the second one is an apple, the third one is an apple, and so on. So you need these two things, and then based on this, you're training a model. Whatever that model is, if this is a neural network, if this is a simpler form of model, that doesn't really matter, but you're getting a model and you're getting some kind of parameters that you have learned from that. So that's the first stage, you train your model. And then the second stage, you actually want to use machine learning to predict something, so you have a prediction phase. So you have some unseen data where you don't know what's the label. I guess this is an apple as well. And you're putting this into the model, and you're then predicting, okay, this is an apple. So this is the second stage, the prediction stage, that normally happens maybe in some instances in real time, because if you have an autonomous vehicle, this should go quite fast, that you have your prediction to, I don't know, recognize what kind of traffic sign you have. What we specifically talk about or use in this talk is actually the classification setting, which is already what you have seen before. So you have maybe an example here of two different classes. So I have bananas and apples, and I want to learn a model that kind of learns a decision boundary, how to distinguish these two classes. Of course, this could be more than two classes, but two classes is always the simplest setting that you can consider. IP protection can also happen for other types of models, but we mostly talk about classification today. Now, in machine learning with security, it's the same as in any kind of other computer system or in any real-life system. It's almost impossible to achieve a perfect security. So what we actually want to do is we want to make it at least more difficult for the attacker to manipulate, or in our case, to actually steal something. So we also have some kind of costs, and the costs, I think Tanja will talk a bit more about that, but in most settings, the cost is actually that our model doesn't perform as well as it would have performed originally. So there's no monetary costs, but you actually have less effective systems. And we can think about attacks on machine learning also on the CIA triangle that I guess most of you are familiar with. And we can look at attacks on the confidentiality, availability, and integrity of the model. Yesterday in the talk, if you were there, you heard a bit about the attacks on integrity and availability, but today we're all about the confidentiality. So what actually can happen in your machine learning workflow? What kind of attacks can you have? So you can have, for example, attacks that happen in the prediction step. You're basically modifying somehow the data that you want to predict, and this is something that you maybe have seen, evasion attacks, adversarial examples that try to predict something different. So you have, I don't know, a panda originally, you add some kind of carefully crafted noise, and it's getting detected as something else. This is some modification you need to do for every kind of input you have. Another kind of attack that you can do is the so-called poisoning attack. In the poisoning, you actually modify the training time. So you actually add some kind of modification on your training data so that the model then learns, for example, whenever there's a yellow post-it on something, that sign is not going to be a stop sign, but it's going to be something else. And then it's much easier to manipulate this. And you can also have attacks on the model itself, so on the confidentiality of the model. That could be kind of on the data that's underlying the model or the model itself. And that would be model stealing or model extraction attacks. What you see on the top, I didn't mention this. So, for example, this was an attack on a Tesla system where they also did some kind of evasion attack, and it's not recognizing the speed sign correctly anymore. What are the assets that we want to protect in machine learning? On the one hand, we have training data. That is a valuable asset. It takes a lot of time to collect training data. It takes a lot of time to label training data. Most of the times you need to pay people to assess the training samples, and then we need to say what class it is, or maybe they need to do segmentation. This is actually done on a really large scale. So there's actually quite an interesting article how this is outsourced to low-income countries to actually scale this up. So this is something, one asset that you could have. Other assets that you could have is something during the training process. So you need to normally say, okay, what kind of model am I going to learn? What are the parameters for the learning process, learning rates, and other things? This takes a lot of time and trial and error to find correct values. And of course, you have in the end the learned models that you want to protect. It normally takes quite a lot of computing resources and also some time to actually train a model. So if you don't have some kind of time warping advantage that you train your model in a different, kind of time that you actually would be very fast, what you normally have to do is to have to wait a long time. And then even if you had such advantages, people start to train deeper and deeper and larger networks. So it's always going to take longer than the newest technologies that you have. So people spend a lot of time actually waiting and just training their models. So this is a very important asset, the trained model, because it took a lot of time and resources to create it. Now you might wonder where actually all the assets in your machine learning process actually where they're exposed. Where can an attacker actually get hold of that? One thing that an attacker could easily use is sometimes people share pre-trained models. So I'm training a model that's, for example, able to distinguish between different traffic signs, and then I'm offering this in the marketplace. Whether this is for free and I have maybe some certain license or actually I charge a fee, this could be one model. And there's actually multiple platforms for this, some that don't charge you anything like the Model Zoo, but also, for example, in Amazon Web Service, you have a marketplace nowadays where you can obtain pre-trained models. And the attacker maybe doesn't want to pay for that, or maybe doesn't want to adhere to the license terms, whatever these are. So that's one way. The other way to get access to something on the machine learning pipeline might be if you use machine learning as a service. So if I'm offering a service where you can send me some input and I give you the prediction, then this is something you can get some kind of hold on that. And there's a lot of providers offering this. You have also, again, Microsoft, IBM, Amazon. They all offer pre-trained models or offer you a way to train models, but you normally don't get really the model. You just get the access to the prediction engine. And then there might also be some kind of machine learning embedded in a certain application or device. Maybe the device is not always as big as this Tesla here, but it could be some smaller device where there is a machine learning model on and it does some kind of prediction, and then you could also try to get it from there and you have some kind of access. So the motivation to steal the IP is you don't really want to maybe pay for querying the model or for actually acquiring first. Maybe there's also some other limitations. If you have an API, maybe it only allows you to do 500 queries a day or something like this, and you don't want to do that. And there might be also further motivations, like actually attacking it in a further step down the pipeline, but we're not really talking about this. We're mostly talking about the monetary reasons why you would like to steal it. As I said before, there might be these platforms where you actually publish machine learning models. So you might have a certain use case where Alice is training a model, and then it's offering it to download, and Bob just downloads the model, and then is illegally redistributing that model. Maybe charging another fee, maybe charging less than Alice did in the beginning. This is actually quite easy for the attacker to steal, because you actually have the model, and you can just pass it on. Maybe you do some kind of modifications before you pass it on, but this is a relatively easy case. The more difficult case is when you actually don't have a copy of the model in the first place, but you maybe have just an API access. So Alice was packaging this in a certain application, so it's kind of within a box, you don't have it directly, and then you apply some kind of model stealing attack. And then again, you would redistribute this. In all these cases, what you would like to show is actually that the model is actually the one that Alice originally trained, and that Alice is the rightful owner. So for the second case, how to actually perform these attacks, these model stealing attacks, basically this just requires me to have black box access to the model, so maybe a prediction API, or I have the Tesla in front and I can just observe what happens to it. And basically I'm able to send queries and I get the responses. And I have maybe some limited resources. Maybe I can only afford to do 1,000 queries a day or something like this. So I'm maybe limited, so I cannot do indefinite amount of queries, but maybe I have enough capabilities to still do this. And then I want to find a trade-off between having a small number of queries that I'm sending and the good performance of the model I'm stealing. There are some types of models that you can steal actually exact. So you can, for example, if you have a logistic regression, rather simple model, I only need one query for each of the learned parameters of that model, so I can actually steal it relatively easy. This doesn't really scale easily for really deep learning architectures where you maybe have hundreds of millions of parameters, and even if you just need maybe 5 queries for each parameter, if you need to send 5 million queries to steal the model, that's maybe suspicious and maybe expensive. So what you do in most cases is that you actually can do an approximation of the model, and you need much fewer queries for that. So basically you query the model, And the data that you use to query and the returned labels from the model, the predictions, this you use to train your own substitute model. So, for example, you send this picture of a cat to the model, you get some kind of probabilities, what the model thinks this input is, and you do this with other samples, with this dog, and maybe you get the same prediction because it's a bad model, but this is basically what you get. Maybe sometimes you only get the label, so you just know it's a cat, you don't know anything else, you don't know probabilities, but this is kind of the information that you get. And from this, you have basically now your training data, you have ground truth because you have these predictions, and then you can train a substitute model that might be up to 99.9% equivalently good as the original with relatively few queries. You still need the computing resources to train the model, but you need not to you don't need to acquire the training data yourself. So there's a few ways how you can obtain, how you can steal, how you can misuse training data and the learned models. Now I hand over to Tanja, who will hopefully tell you how to protect against that.
Okay. So I will try to now tell you a little bit about how to defend against model stealing, for example, and other types of unauthorized usages of machine learning models. So I want to start with threat model that Rudolf already presented. So we will take the first scenario in our threat model, where Alice has her model and shares a legal copy with Bob. And then Bob has the full access to this model, can do anything with it, but decides to share it without authorization of Alice. And this is called now illegal distribution. So it's pretty hard to actually defend against this because we are giving full access to Bob. But what we can do is actually figure out if the model that we shared and that Bob distributed is actually belong to Alice. So how do we do that? One way to do is model watermarking. So watermarking is actually motivated by watermarking in other domains, such as image watermarking, that you might be very familiar with. So it's a way of hiding some kind of information in the content that allows the owner of the content to prove their ownership. So in this case, it's maybe very obvious that there's a watermark on the image, but what we kind of want to think about is way less perceptible changes in the content. So maybe just a specific pattern of changes, of the pixel changes in the image, something that is not obvious to the observer. One interesting thing is that actually, even before the image watermarking, this type of concept was applied in geographical maps. So the creators of geographical maps back in the day actually wanted a way to stop or at least detect if somebody copies their maps, because this was a very hard job to actually get the geographical map. So what they did is they would put some kind of trap streets, so-called, so kind of fake streets or fake lanes or even fake towns into the maps. And with this information, if they see these fake streets in some kind of map, they would be able to claim it's their original map. So this same idea we want to apply on machine learning models. But how to actually hide some information in the machine learning model, or specifically in neural networks, because this is area which is mostly applied on neural networks. So even if you know little or nothing about neural networks, I guess you can imagine it literally as a network of a set of neurons that are essentially computational entities or functions that have parameters. And in state-of-the-art neural networks, we have millions and millions of those, which means that this is actually a good way to hide some information inside of those. And we can obviously take a model, take the weights or parameters, and change them explicitly. But this is not such a good idea because this decreases the model's performance. So what first authors of some watermarking technique for machine learning models did is they thought, okay, let's take a network, let's train it, and during the training process, we will change the weights in a very specific way that at the end, if we look at the weights of some model, we will be able to see these specific modifications and be able to claim that this model actually belongs to us, so that we made these specific modifications. So this means that for the extraction of a watermark, one needs the full access to the model. So we really need to be able to look at the weights of the model. And this is why it's called white box watermarking, because we actually need a full access. So to see how the white box watermarking looks like is the model owner trains the model and embeds their watermark inside and then shares it. And then the adversary, if there is some kind of unauthorized redistribution of the model, it needs to be available in a full form, in a white box, so that the model owner can actually extract the model. But if you think about it, this is not such a realistic scenario, because if you are adversary and you have a model that you want to share without redistribution, you would likely do it in a less obvious way, let's say. So what is more likely is that you will, as an adversary, you would share it through an API service that only provides this model as an service that allows queries to the model and obtains the predictions for whoever. And now it's actually a harder job for the model owner to prove their ownership, because they cannot anymore look into the weights of the models, but can only access the predictions of the model. So this is actually also possible through a concept that is actually well known in adversarial machine learning, and it's called backdoor attack. So what is a backdoor attack? I will just try to say in a very few lines. The goal of a backdoor attack is to cause some kind of unexpected behavior of a neural network that is wrong. So what the backdoor inputs do is they look like normal inputs, but they're modified slightly, and they make the model behave in a wrong way. So you can see that on clean inputs, the model would give a correct prediction, but in case of backdoored input, it's a wrong prediction. And then somebody who wanted to make a the black box watermarking method thought, okay, this is actually a very cool property, because it means that these backdoor inputs are somehow hidden inside of the model. So maybe let's use this backdoor attack for protection purposes. And this is exactly what most of the the black box techniques are based on. So they create some kind of trigger images that are embedded into a model that create very specific responses from the model. And from these responses, the model owner can detect that this is indeed their model. So we can have different types of triggers. This is mostly done for image classification problems. So we can have something completely out of the distribution, something that is not in the training set for the models, and label it as something from the training set. Then we can have something from the distribution, for example, a dog picture that is labeled as a cat, so wrong prediction. Then we can have a pattern-based, so some kind of pattern over the image from the training set, or some kind of noise on top of the image, or perturbation in the image. So all of these are possible to actually achieve black box watermarking. Okay, and now I would like to talk about the second case that we have, and it's when Alice shares only the API of the model, so not anymore the full model to some recipient, but rather API where you can query the model and obtain the predictions. And then Bob performs the attack where they try to steal the model functionality from this API. So kind of try to recreate the same functionality from the model by querying it. And then this is actually how, so the watermarking that I presented so far doesn't actually work well with this. Why? Because model stealing does not take, it's just, if you remember from the slides from before, from Rudolf, it's just the approximation of the model. It's not the exact model. And these trigger images that we are trying to embed as our watermark are actually lost during the process of model stealing, because there are very specific functionalities that don't anymore exist if you try to approximate the model. So we need something else. We can, for example, take the API and so not change the model at all, but rather make our API say, okay, put some wrong predictions in a set of queries that one user does. And of course, this is lowering the performance of the model. Not on the model, but of the API service that is providing the functionality. But it does allow to kind of mark the output. And if the model stealing happens, it means that the attacker who is trying to steal will actually embed these kind of wrong predictions into their stolen model, and the owner will be able to detect it. This is still a reactive defense. What does it mean? It means that we cannot stop the model stealing with this. It can still happen, but we can detect if it happens. There are ways to do protection against model stealing proactively, and this is where we use so-called monitors. So what monitors usually do, they try to see the behavior of the user who is querying the model. So how do these queries look like? And if in any way these queries are found suspicious, the API can behave in a certain way or raise a flag or stop the producing the predictions and so on. So, for example, the monitor can try to see if the distribution of the queries on the model is actually very different from the original training data. And this is kind of a trigger to say, okay, we have some kind of unexpected behavior or like adversarial behavior on the API. So yeah, I hope you at least got intuition or like a little overview of how we deal with different unauthorized usages and model stealing. So of course we can approach it in different ways. As I said, we can do it reactively, so only detect it, or proactively to actually try to stop it. And we always, or almost always, actually trade off some accuracy of a model to gain protection over the model. So, and this is something that we have to think about when we design the whole system, because we want to, of course, lose at least lose the least of the model's performance. Of course, there is many more methods that we didn't mention now, and this is actually a very active research area because it's only about 5 years old, and there is constant arm race between the attacks towards this type of methods, and then in response we have the protection methods that are kind of upgrading or just different to protect against different types of attacks. So thank you very much for your attention. And yeah, just for this is our team. We are in the machine learning and data management team, and yes, we work on different types of protection and attack methods on machine learning. So security and privacy in machine learning is our our major focus area. So thanks you.
Thank you, Tanja and Rudi. So we have some questions in Slido, and I start with the first one. Are there already a lot of models being illegally traded, or is this more of a future issue?
So the question is if it's already applied, or is it a future? Yeah, I mean, kind of both. So I think it's a raising issue, basically, because there is more and more necessity of kind of reusing certain models, for example, using already pre-trained models. And So if at some point you, or even when you actually have to charge for your model's functionality, right? And then there's a great incentive of protecting in some way. So maybe it's not I don't know if Rudi, you maybe have a good example of where it's applied right now, but I see it as a bit more of a future issue than right now.
So I think it's still missing this, I don't know, these few cases where you have seen people actually stealing.
Continue.
But the more and more we are starting to depend on high quality models, I think this will increase a lot. And of course, nobody, as with almost any security incident, nobody's proud to say, okay, my model was now stolen. So it doesn't maybe make the news so much yet, but at least we are thinking that this will come.
Yeah, so and also what might be the incentive of model stealing is that then it's actually easier to perform other types of attacks, to try to make the model actually misbehave. So in a way, if you want to compromise a certain service, right, that is based on machine learning. So this is another incentive where these model stealing attacks could happen.
Yeah. Okay, thank you. Next question is, would an Austrian court even accept trigger images as proof for stealing a model? Are there already rulings on this? Do you know?
I think what you definitely would need is to add some kind of, I don't know, kind of depositing of this knowledge that you had at a certain point. So maybe at a certain point I go to a, I don't know, notary public, or I use a blockchain or whatever to deposit, okay, for this model, these triggers would yield a certain response, so that I prove I had this knowledge at a certain time earlier. This can be in kind of evidence, not yet, of course, a formal proof or anything, so there's no formal proof saying that this is really my model, but it would be some kind of evidence. We have not really heard of any court rulings against model stealing yet, so I don't know if it would really hold, but it would basically, I don't know, it would need to be seen in court, but I guess you would need to at least deposit the kind of the evidence that at a certain time I had a certain knowledge about the model and I was not, I don't know, fabricating this knowledge afterwards, because I could also find weird behavior of the model, trigger images after the model was already published. So I could also do that, but if I deposit it and I knew it 5 years ago and Tanja maybe knew it only 1 year ago, I have a better evidence.
GitHub Copilot uses the OpenAI Codex model to suggest code to programmers. Any ideas on how this could be used as supply chain attack to create backdoors? Again? Yeah? Long question.
So slightly orthogonal topic to what we discussed, because the backdoor attack is basically what Tanja also mentioned as a defense, basically. But a backdoor basically would mean if I have a certain pattern, I want the model to behave in a certain way. And things like this is actually the perfect example how to modify this, because I could just write my own, I can make my own GitHub repository that at some point gets harvested, and I can, in my code, kind of embed this behavior, and at some point, GitHub will train the model again with my data, and then I could embed this. Another thing where you could easily attack is, for example, I don't know, spam filter. If I, on purpose, label some things wrongly, and then at some point Gmail picks this up, I might have embedded a backdoor there. In other settings, it's more difficult. So with Tesla manipulating, I don't have a public API to send pictures to Tesla so that they train it wrongly, but for some settings like this, where you rely on user-created content, it's actually doable.
Okay, where, in which sector do you see the biggest risk for machine learning attacks? Maybe an example?
Well, I think one very good example is autonomous driving. So, because it obviously draws some other issues with that, such as safety of humans. So if the models that are inside of the autonomous vehicles misbehave, this is a really big problem. So this is, I think, one very good area where the security in general of machine learning systems should be applied, and I think is, actually. And otherwise, I think also any type of systems that are actually learning from some kind of personal data. So there is always some kind of incentive there for the attackers to try and manipulate this type of systems for the purpose of trying to find something about the individuals that are inside of the system's training data. So these would be good examples of where the security in machine learning could be applied. Yeah.
What would be the value of a normal performance loss in real models? 5%, 40%?
The loss in?
The loss in real models.
Due to the watermarks.
Of a normal performance loss in real models.
I guess that's a range, but it's I think it's like a few percent. It's not a lot. So I guess the question is about if we embed a watermark, how much does the model performance drop? Yeah, it depends on the scheme. So usually, if we have white box watermarking, this usually means that we can preserve the accuracy better because we have more access and more control. But in black box, yeah, it's a bit more, but it's a matter of few percent, I would say, in accuracy.
Or sometimes maybe even less, so it might be even 0.5% or 0.25%. So it could be very, very minimal. It depends, of course, on, for example, what Tanja talked about, this proactive defenses. Maybe there you would lose a bit more, but in the watermarking it's very minute.
Okay, and one last question. Have you joined the Adversa AI competition or ever heard about it?
I haven't joined the competition, no. Have you?
Maybe you should.
Yeah.
Maybe you should, yeah.
Yeah, good idea, thank you.
So then, one last applause for the two. Thank you.